We're going to talk about some forces that affect motion here on the planet Earth. Three major forces that I want you to be masters of this year are gravity, friction, and then air resistance. Now, we've talked about gravity before. You've been told that gravity is a natural attraction between any two bodies of matter. It can be from the smallest atom to the largest star system. If it has any kind of matter, it is going to be attracted to any and everything else that has matter. But there's two stipulations. The strength of that attraction is based upon how large the objects are and then how close they are to each other. Okay? While I might be attracted, say, to this board behind me, the Earth is a larger object, so my attraction to it overpowers my attraction to the board. One of the examples we've talked about in class is that if we strip the universe of all matter, of all stars, suns, comets, aliens, planets, asteroids, meteors, everything, and we put two items on opposite ends of the universe, that even across all them light years of distance, they would still be attracted to each other and slowly start moving towards each other. Scientists also think that once an object gets to about a half a mile wide, it is now sufficiently large enough to start attracting objects to it and pulling objects in. This is important to their early theories about how the Earth was made. Now, friction is a force that is caused when two objects come into contact with each other. Whoop. There's a couple different types. There's the friction that we talk about when we rub our hands together and our hands get hot because they're rubbing together. But there's also a type of friction called static friction, and that's what lets us just pick things up. That's what we call grip, and it lets us hold things. For example, this marker. The last major force that I want you to really know about is air resistance. And really, air resistance is just a special type of friction. It is the friction with the air. We've discussed before about how air is matter. It has weight, it has mass. When you wave your fingers, you can feel it rubbing through your fingers. Okay? When that wind you feel, that's air resistance. That's the mass and the resistance caused by the air coming in contact with the object. So let's take a look at my little diagram here. This is me on the golf course hitting a golf ball. Okay. There. Now it's me on the golf course, got my belly, hitting a golf ball on the golf course. The thrust and the forward motion is generated by my swing. And we, right there, have examples of Newton's laws of motion. Okay? That mass times force equals acceleration. It's got a small mass, there was a high amount of force applied to it, it accelerates, hopefully several hundred yards in a straight path. However, we said Newton's first law that an object has the tendency to travel in a straight line forever unless it's affected by other forces, that idea of inertia. Well, fighting inertia, the golf ball's inertia, we have gravity that is always pulling down on every object on our planet. Gravity is actually what causes objects that are fired in the air, whether it's a golf ball or whether it's a football thrown or whether it's a missile launched out of the ocean. It's those things it's gravity that causes those things to have a curved path that come back to the Earth. The other factor that affects the motion of my golf ball is air resistance. Now, this is super high level physics that you'll talk about in high school, but this can change and be a different factor depending on how cold the air is. Remember we said when we were talking about weather that colder air is denser. The molecules are drawn together, it's thicker. There's going to be more friction, more air resistance with colder air than hot air that's expanded and has a low pressure. The last friction is just surface friction with the grass. When my ball actually lands and heads towards the green, every time it comes in contact with one of those blades of grass, that grass rubs against it, slowing the motion even more. On Earth, gravity, friction with the surface of the Earth, and then air resistance eventually overcome any kind of force that we might be able to apply. And if we don't continually apply force to an object, it will come to rest. In space, it's a little bit of a different story. That's how we keep satellites in orbit. Now, you guys are going to do this one with me. take a moment, pause if you need to, and identify this diagram, or draw this diagram out. We're going to identify the forces that are going to affect the motion of this Tonka truck. Now, this Tonka truck could have been its direction of motion, the thrust that generated its motion could have been a series of things. It could be rolling downhill. It's not. It's on a flat surface. It could be pushed by your little brother or sister. That part of it is really inconsequential. What we want to look at is what is going to slow up its motion, affect its motion, and stop it from moving. First thing, like we just said, gravity. Gravity is always pulling down on the object. Because gravity is pulling down, it's going to force the wheels to come in contact with the road. That rubbing action, whether it's with the road or whether it's the sidewalk or even your table, is going to cause friction. And the truck is going to lose some of its energy right there. And even though it's only a Tonka toy, and even though it's a small little truck, and when you push it, it still comes in contact with the air, and there's still going to be some kind of air resistance that's going to sap this truck of some of its energy and slowing its motion. Now I got a tricky one for you. Tonight for homework, what I want you to do, I want you to consider this problem. How about a fish? Draw the fish out. I want you to list the forces that are affecting the movement of this fish swimming. And I also want you to show the direction that that force is pushing. Go back to the example of the Tonka truck. I showed that the air was pushing against it just as the truck was moving against the air. For every action, there's an equal and opposite reaction. We'll look at your diagrams tomorrow. We're going to share a few on the Elmo, and then we're going to do a couple labs and take it from there.